everyone. Welcome back to my math teaching online today. In this video today, I will get right into the application of logarithmic function and exponential function in the course of Introduction to Calculus. Now, yesterday I was explaining to you about the technique of how to differentiate the exponential function and logarithmic function. So the lesson today will continue with that, which is now we will use the technique of differentiation put into the application of the word problem to solve our real life problem. And you will see mathematics play a huge impact on problem solving from chemistry topics to physics and to economics topics. So let's take a look at the equation on the board today. Before to get into the application of it and solve the problem, I would like to explain to you, introduce to you the formula and where the formula come from. Where do we have that equation so that we can put in our word problem and solve for it, right? And everybody curious want to know about that. And that get into a little bit of concept, right? Okay, so let's get right into the equation here. You see on the board, I have a function f, t represent the time, respect to time, equal p0 time with e to the k times t. So my question to you, where is this formula from? Where is this formula from? Now, if we don't know it, we still can solve the math because our mathematician has derived the formula for us. So all what we do is copy it and solve our problem. However, if we're more curious, we want to know a little bit. So let me explain to you, right? Any exponential function, we're talking about the rate of change of a certain amount of rowing, right? And in rowing, we call it exponential row. And why we call exponential? Because let's say a simple example, let's talk about money, okay? So if you are deposit the money in the bank, you accept that you earn the interest, and the first level you learn is the simple interest. So if the bank give you the rate of 2% per year or 3% a year, then you multiply your original amount with the rate of interest. And simple interest show you that each year, for example, if you earn $50 or you earn $100 a year, your interest is stay the same. If you earn it in 3 years, if you put money in the bank in 3 years, you time with 3. If you put it in 10 years, you time with $50 time with 10. So that stay the same. And that is not exponential row. That is just the rate of simple rowing multiplied with the time adding into it like 3 years, 4 years, 10 years. So the rate doesn't change, it stays the same, $50 per year you earn, right? Now, the difference between compound interest and simple interest is in your compound interest, your money is not stay the same, and your interest, therefore, is not stay the same. You earn the interest on the top of each other, right? So on the top of each other, so your interest grow in a huge rate. And that's why instead of multiply, you power your number. And you know the power, if 2 to the power 2 is 4, then on the top of it will be 2 to the power 2, and then time with power 2 again, then you have 2 to the power 4, which is 16, right? So therefore, in math, they represent this row, and you see this is exponential row, right? And if this function is not growing, but it decline, so in the case of decline, like a carbon 14, can decay over the years, right? Substance like uranium, whatever in chemistry, right? Any substance can get decay. Or your car value over the years can get decline as well. Instead of you bought the car at the beginning $30,000, over the years went by, the car is going down, never stay the same anymore, right? In that case, we have a exponential decay, not growth, but decay. And therefore, you have a graph look like this, right? Get decay until get down to the zero value. There's no value anymore, right? Close to zero, never reach zero, but almost zero. So any exponential function, let's say a symbol function, you have the y equal a to the power x. So the a here, any number, 3 or 4 or 5, and then the x here, any number, 2 or 3 or 4, whatever, right? This is a normal exponential function. However, if you're talking about the rate of change in calculus, you're talking about the rate of change over the times, then this y no longer just symbol y, not a certain amount, but it will be f, represent a function respect to time. So now I change the y here, become f of t equal. Now the a is the money you put in the beginning, right? Or the population, let's say the population of the town is 1,000 people. That we call a population, and we represent by P0. In a way we talk about money, we call a principal amount, P0. You invest in the bank 1,000 or 500 or 200 at the beginning. So that principal amount, we change it become a principal amount and represent by P0 as well, right? So this P0 is very much depend on whatever you want to name it, bacteria row or money row or your investment rowing, right? Whatever. So this just P0 stand for the original amount. And now let me derive this formula come from where? So recall. Now we're talking about future value in money, right? Future value, the formula you learn in Math 12, the future value equal the principal amount, let's call it P0 as well, right? And FV stands for future value. So this P0 is the principal you invest at the beginning. Time with 1, adding with the rate of interest the bank give you, could be 2% or 2%, whatever, which is represented by R rate, right? And the rate here also depend on your compounded. If you compounded money monthly, you will divide by 12. The rate of the yearly rate will divide by 12 months. If you put in the compounded quarterly, then you divide this rate by 4. If you invest in daily, then you divide this rate by 365 days in a year. So therefore, in general, we just say R over N, depend on your compounded monthly or quarterly or yearly, right? And because the rate you divided, then of course the time here, T, you have to compensate by your division as well. If you're talking about year, then just 1 times T, which is 1 year. If you're talking about 4 quarterly, 4 periods a year, you have to time with 4. And if you talk about, you divide this rate by 12 months, compounded monthly, then you multiply with 12 for the periods of a year. Instead of 1 year become 12 periods a year, right? And if in 2 years, so the T will change it by 2 times with 12 months, which is 24 periods. So the T and the N here is flexible, right? And if you divide this by 4, you time back with 4 to get the 4 period per year. if you divide by 12, you substitute n by 12, you get 12 period per year, right? So this is a compounded formula in money earning of interest, what you have learned in the past, right? And the one here, actually, it just represents if you deposit in 1,000, you have to tie back with 1 to get 1,000, adding with your interest, right? If you don't put a 1 in here, then you just talk about the interest and you forget to add back to 1,000. So the 1 here is just the convenient way for you to multiply the P0 back to here, to add back to here to get your whole future amount. If you don't have a 1 here, then the whole thing here just represent your interest money and not including the principal money. But remember, this is the future amount. I mean, you have to add back to the 1,000, and that's why you have to put 1 in here. That's on the formula come from. Okay, so I explained a little bit about the compound interest formula for you. Now, why do I do that? I do this with a purpose. So let's take a look why. Go to the next bar, I will explain why. Okay, so if you look at here, remember yesterday I will explain to you where the E number come from. And I said that if you have 1 adding with 1 over 10, and you have power 10, then you calculate this number become 2.59 or something. 1 adding with 1 over 10 to the power 100, sorry, divide by 100. And this get into 2.64 or something. And then 1 adding with 1 over 1,000 to a power 1,000, then it get close to, this is 7.0 whatever, right? And this pattern continue until you hit 2.7, 2818, and irrational numbers. So keep growing, right? The same pattern and blah, blah, blah. Okay, so remember this number is we call an E number, right? So if you do like this, you will see your number never get result in 3 or in 4 or less than 1. It just stay the same pattern, get close to 2.728. And that's why this number very special number and the E number come from. Mathematicians name this is a natural number E, okay? Why do I mention about this? Now, if you look at this formula here, compounded money formula, do you see it's similar? This is 1, this is 1, R over N, 1 over 1,000, 1 plus 1 over 100, 1 plus 1 over 10. So now you see that this is the same pattern like this number, right? Now, we're talking about a function respect to time. So instead of future, now the same, similar, right? We have a function of future value, but don't forget it's respect to time. At the beginning, you put in principal amount P0, time with the rate of change, which is this one. But if you let this rate of change, the time here, and here, it go to infinity, which is you don't know how long. It could be 1 year, 2 year, or 3 year. Or if you're talking about subton, it could be 30 years or 1,000 years, right? So if you let this n go to infinity, it means this number down here getting 1,000, 100,000, 10,000, 100,000, million, blah, blah, blah. This number stays the same. It's going to get close to 2.728. So you can replace the whole thing here by what? If you let n get into the infinity, go to infinity, because the time you don't know, right? Then the whole thing here, you can substitute by the E number, just like this, right? And therefore, you see this C time with E. Now the K here, the same like the N here. So you can put NT or KT, I don't care, right? So that is where this formula comes from. So I explained to you the concept. Where do we have this formula? Once you understand the concept already, you know where this formula comes from. We will get into the next video, which is the application of this formula to find any rate of change, any money growing or any bacteria growing in the lab, or any car depreciation value going down over the years. Everything is revolving around this kind of concept and this kind of equation. So stay tuned for the next video. We'll get right into the application of it. I hope now all of you accept this formula, right? And understand it as well. We not only accept it, but we also understand it where it came from. So I hope you enjoy my teaching video, and I will see you in the next minute. For the next video, we will solve the word problem involving the exponential, the derivative of exponential function and logarithmic function in calculus. And don't forget to give me a subscribe if you like my teaching, and have a good day, and I see you in next video. Stay tuned for that. Thank you for watching. Bye for now.